This is 40 Days of Chemistry, Part 19, this time looking at indicators. Now, as the syllabus says, indicators were identified with the observation that the colour of some flowers depends on soil composition, and the most famous example of this is hydrangeas. In alkaline soil, their flowers are pink, in an acidic soil, their flowers are blue, and depending on the pH, you get a range of colours from pink to blue, right through the purple in between. And this is what inspires science to look at chemicals that maybe change colours in different pHs. But just for your information, the actual colour of the hydrangea flower isn't really dependent on the hydrogen ion concentration. It's actually dependent on the aluminium ion concentration. It's just the fact that in acidic soils, the aluminium ions become available for the plants to absorb, hence turning their flowers blue. And that's something that links to our acid rain topic. We know that the acidic rain can release aluminium ions from the soil, and therefore that can actually poison some plants. In hydrangea's case, though, the aluminium turns its flowers blue. Common indicators. You need to know these four common indicators. You need to know their names, you need to know their colours, and the pHs at which they transition from colour to colour to colour. And it's important to, when you're describing this, get the order right. So for example, bromoethanol blue changes from yellow to green to blue at 6.2 to 7.6. Notice that I went in order of colour, from acidic colour to in-between colour to the basic colour. And when I mentioned the pHs, I said the acidic one first and the basic one second. So match the colours you say to the transitions you're saying in terms of pH. And for your information, there's universal indicator as well. It's got a range of colours because it's actually a mixture of different indicators designed to change colour at different pHs. But these are the four you have to know: bromoethanol blue, litmus, methyl orange, and phenolphthalein. Indicators and Le Chatelier's principle. Now, indicators are chemicals that exist in equilibrium with hydrogen ions, i.e. hydronium ions. There's an example indicator equilibrium there. And in this case, HX, the indicator, is a weak acid, and X- is its conjugate base, so it links into Brother-Solari theory as well. This is a good example of the interconnectedness of ideas in chemistry. Just like buffers, indicators require understanding of equilibrium, Le Chatelier's principle, and Brother-Solari theory. But the thing about indicators is the acid and its conjugate base have different colours in solution, and that's why they can be used as indicators. So in an acidic solution, the hydronium ion concentration is high, and thus via Le Chatelier's principle, equilibrium shifts to the left to reduce that hydronium ion concentration, thus making more of this chemical HX. Therefore, the solution turns red in acidic conditions. However, in basic solution, the concentration of hydronium ions will be low. This equilibrium will shift to the right to produce more of this green X- ion, and therefore the indicator turns green in basic conditions. Moving on, we have making a natural indicator. We made natural indicators by boiling up and mashing up a range of darkly coloured fruits and vegetables. We extracted the juice, then added them to a range of different pH buffer solutions to observe the colours. Now, the ones we decided were useful indicators were they either had a range of different colours at different pHs. For example, here, red cabbage, and it's useful as an acid-based indicator because based on the colour you see, you can pretty much tell what the pH is. But some other indicators can be useful even if they've only got one colour change, such as things like methyl orange, bromoethanol blue, and phenolphthalein. And some of our indicators had one distinct colour change at a certain pH, and that can be useful in things like titrations, where you just want to know that when the reaction or when the solution reaches a certain pH. Less useful indicators either have the same colour at different pHs or non-distinct colour changes. They change from maybe purple to slightly less purple. They're not very useful indicators. Using indicators. Indicators can be used in the form of solutions or test strips to test the pH of swimming pools. In swimming pools, too acidic can damage equipment and irritate skin. Too basic can lead to cloudiness, and both acidic and basic conditions can interfere with the effectiveness of the chlorination. You can use them to test the pH of fish tanks, because many aquatic organisms require certain pH ranges to survive. If you're testing soil, you need to mix the indicator with the soil, then sprinkle a white, say, barium sulfate powder on the surface to soak up the indicator and reveal the colour. And that's because the indicator inside the soil is hard to see the colour because the soil is dark. In the lab or inside, indicators can be used to show if a spill has been neutralised, and they're also used in titrations where you want to match the equivalence point and the end point. Just some example HSC indicator questions. Have a look at this question, pause the video, and then press play to see the answer. This question is testing your understanding of pH changes and pH colour changes. So if you think about this question, solution was yellow in methyl orange, so it had to be in this yellow range. It was blue in bromoethanol blue, so that reduces the range it could possibly be a little bit further. And it was colourless in phenolphthalein, which is in here. The only space where those three things, yellow, blue, and colourless, overlap is this range between 7.5 and 8.5. Have a read of this question, think what your answer will be, and then press play for a discussion of the answer. The best way to solve these sort of questions is to go through and for each of the colours figure out what pH was going to be. For solution A, it must have been greater than 4.4, greater than 6, greater than 9.6, greater than 12.4, so overall we know it had to be greater than 12.4 pH. It was basic. It was a valid conclusion to assume that it was basic. For solution B, greater than 4.4, greater than 6, greater than 9.6, but less than 11, that acceptable range is 9.6 to 11 in terms of pH, but once again, that makes it basic because basic means pH greater than 7. However, solution C, we've got greater than 4.4, greater than 6, less than 8, and less than 11, so the range the pH must have been was between 6 and 8. And that means it could have been acidic, pH 6, basic, pH 7, basic, pH 8, or neutral, pH 7. And therefore it wasn't valid to assume that chemical was basic because there's not enough information to make that conclusion. It could have been acidic, basic, or neutral. Alright, have a look at this question, pause the video, and then we'll discuss the answer. With this question, it requires you to know what ammonia and oven cleaner, lemon juice, and hydrochloric acid are. Hydrochloric acid, 0.1 molar, should have a pH of 1. Lemon juice will have a pH in the range somewhere between 1 and 7, not 100% sure, depending on the concentration of lemon juice. Water, we know though, had a pH of 7. Ammonia, being a weak base, will have a pH somewhere between 7 and 14. And oven cleaner is usually a strong base, and therefore it's going to have a pH close to 14. To answer this question, you've got to note that acidic is pH less than 7, neutral is pH 7, basic is pH greater than 7. This indicator says for a strong acid or even a concentrated acid with low pH, it's going to be red. A weaker or dilute acid is going to, with a high pH but still less than 7, is going to be orange. So yes, it is pretty good to distinguish between different acids, but because the water and the two bases were yellow, it can't distinguish between basic and neutral solutions. And even still, because we don't know the actual pH of the lemon juice, there might be a range in here of acidic solutions, say pH between say 7 and 5 for example, that might be yellow as well. We haven't got enough data, so we can't be sure it can actually distinguish between acids, bases and neutral, as far as I'm concerned with this question. Have a look at this question, think about the answer, and press play for my discussion. With this question, you had to figure out when it would form a yellow solution. The trick for this question was to remember, and you'd have to know these three indicators, that they transition. They go from red to orange to yellow, and from yellow to green to blue, or from colours to pink to dark pink. And therefore, these regions here in the gaps, which are orange and green, they can't be forming a yellow solution. The only yellow solution will be where there's complete yellow overlap with colourless, which is pH about 4.5 to pH 6. That's the end of the indicators topic. Next will be esters.